Okay, so let's begin the second part of today's lecture. I'm going to start with a Fermi function. So, let's see. Okay. So since I'm saving all the voices and PPT slides in cloud, so it will take I guess 1 day to have I recorded a movie clip. So that recorded movie clip will be posted on iCampus maybe tomorrow or later. So it'll take a few days. And let's see. Okay. Now it is time to understand the physical meaning of Fermi functions. Why Fermi function is necessary for what? Previously, I mentioned that uh, in pure semiconductor material, the band diagram can be drawn like that, two parallel lines, E sub C and E sub V. And here in conduction band, well, at 0 Kelvin, since everything is frozen out, so no electrons available in conduction band at 0 Kelvin. However, at room temperature or at 300 Kelvin, 300 Kelvin, a few electrons available. Not a few actually, right? So the number of electrons in intrinsic silicon material, the total number of free electrons per unit volume is 10 to the 10 per cubic centimeter. So we know the total number of free electrons in conduction band. But question is, at each energy state, again here, y-axis, I didn't draw it, but you should imagine the y-axis on this energy band diagram, indicating energy of electrons. So each energy state here and there, how many electrons are found at each energy level? In other words, we know the total number of electrons. Say if donor concentration is 10 to the 16, then the electron concentration is 10 to the 16 at room temperature, because all the donors are fully ionized. However, my question is, what about this? At each energy state, how many electrons can be found? Each energy state here and there. Can you specify how many electrons can be found at each energy level in conduction band? Again, can you answer how many electrons can be found at each energy level in conduction band? Since you know the total number of electrons in conduction band, which is 10 to the 10 in pure silicon material, or 10 to the 16 if your donor's concentration is 10 to the 16 at room temperature, you know the total number of electrons. But my question is, how many electrons at each energy level, not in whole region of conduction band? What kind of information do we have? Well, one analogy for looking for the answer to my question can be found in a baseball stadium. If you go to the baseball stadium, there are a whole bunch of people, audience, how they are seated, and they have a seat on an aisle or on a chair. Since the audience have his or her own ticket, his designated seat, he will take it. What happened to the conduction band as well? there are 10 billion electrons. 10 billion people are available in conduction band. How they are seated? Well, definitely they should take each energy state, single energy state, and they will take it. How they are seated out. Going back to the baseball stadium, the rule where you are seated is described on your ticket. Seat number. Suppose that 1A10. And look for the 1A block and take a look for the 10th seat. That's your seat. What about the electrons in conduction band? How they are distributed out and how they are seated out? What kind of rules are there? So going back to the baseball stadium again, when we first build up the baseball stadium, the designer, the architect has designed how the seats are distributed out in the baseball stadium. And it is all set. We cannot change it. Now let's go back to the silicon material again. How the energy states are distributed out or designed in semiconductor silicon material. My question is how this is conduction band edge and this is valence band. How these energy states are distributed out. My question is the energy difference between two energy states. Going back to the stadium, there are a whole bunch of seats. This is 1A block, and there is another block. You guess how apart the chair seats are designed away from the others. And what about here? How much energy difference between two different energy states in conduction band? So it's you can find it. There is an analogy. How the chairs are distributed out in this baseball stadium is determined by the designer architecture. What about here? In solid state silicon material, how the energy states are distributed out? You should go back to the quantum mechanics. And when we build up the crystalline silicon material, remember this silicon material, two silicon materials are very apart, and the physical distance in between two silicon atoms is infinite. Then we can say that this silicon is isolated. Then the outermost electron is now moving around the silicon atom, and it's a 3s and 3p orbit. But once these two electrons get closer and closer, and in the end, they're gonna build up the solid state silicon material following the diamond structure. As we have learned, the two face centered cubic structures are overlapped, right? So following this rule, the silicon atoms are placed here and there. And what happened to the energy state of each electron to build up the covalent bond? Previously, I said here is a 3s 3p orbit, and in the end, since those two silicon atoms are interacting to each other, so these 3s 3p orbits are combined together, resulting in newly created energy state. There is a two wave. Once two waves are combined together, we will see the much higher waveform. This energy level has never been existed in previous two waves. But once they are combined, we will newly create the new energy state. Same thing will be happened in the silicon material. Once this silicon atom, two silicon atoms are combined together, getting closer and closer, new energy states are created. That new energy states and have already drawn here and there in conduction band. Okay, many new energy states are created. Then, based on quantum mechanics, you may estimate how much energy difference can be found in these two different energy states. We won't talk about too much details how to calculate the energy states in conduction band. But this whole bunch of information, how energy states are created in conduction band, can be described as a density of state. So how many energy states available per cubic centimeter per unit energy? So again, y-axis indicates, energy of the electron, right? So per one electron per unit energy range, how many energy states are available? How dense the energy states are existing? Okay. Then this density of state can describe this physics. What about the baseball stadium? What is the density of state for the chairs and seats in baseball stadium? Density of state of stadium. Can you write down the equation for this? Maybe yes. Energy of chairs, right? And zero energy level there are 1, 2, 3, 4, 5. And energy 1, 1, 2, 3, 4, 5. And energy 2, 1, 2, 3, 4, 5. So it is constant, right? As 5. So this density of state for this baseball stadium is quite simple. Whatever the energy is, the number of seats is 5, constant function. Going back to the silicon material, density of state for silicon is constant function? No, the quantum mechanics said the density of state for pure silicon material is following the square root NH minus E sub C, and a few coefficients are available here. So density of state for silicon is proportional to the square root times square root of NH minus E sub C. Baseball stadium, the density of state is constant. Okay, so now going back to the original question again here. My question was, how many electrons can be found at each energy level instead of estimating or counting how many electrons are there in conduction band. Instead of in conduction band, at each energy level, how many electrons can be found? Going back to the baseball stadium now, how many people, audience, can be found in this baseball stadium? Do you have any good idea to guess how many people are there? The data analyst will do this. Let's count the seats at each energy level. So that is equivalent to the density of a state. And now let's look for the probability of looking for a person on each seat. What is the probability value for this specific chair? Say 1/810. Maybe 30%, 20%. Okay. Now let's going back to this question again. At each energy state, specifically at this energy state, what is the probability value of finding out the electron? Going back to the baseball stadium again, the big data guy will claim this theory. Let's set up a CCTV camera onto the stadium, and let's record what happened in baseball stadium for 24/7 from Monday to Saturday, from 10 to 10, we can record everything. Then we can guess how many seconds or how many minutes or how many hours a certain seat has been taken by person. Then for 365 days, a certain chair tagged as 1A-10, that chair has been secured by a person for 2 days. So 24 hours are seated with a person. Otherwise, no person in that chair. Then we can say that, that probability of finding out a person that a specific chair is 305 days, only 2 days. So this value, 2 over 365, is the probability for what? For estimating this chair has been taken by a person. Now let's going back to the energy state in conduction band again here. We know how the energy states, we know the chairs in conduction bands are distributed out following the density of state. And the question is, at each energy state, what is the probability of finding out the electron? Going back to the baseball stadium, we can use a CCTV camera and we can estimate the probability of each chair. What about the silicon material? Do we have that kind of a multifunctional camera to guess and estimate the probability value of finding out the electron at each energy state in conduction band? Is it possible? Yes, it is possible. The kind of a luxurious camera can be made by physicist Fermi. So Fermi has built up his own function named as Fermi function. And this Fermi function can give us some idea. What kind of idea? The probability at each energy state. Okay. So here is a Fermi function. So Fermi function is described with exponent 1 over 1 plus exponential energy minus EF over KT. So K we have learned, Boltzmann constant. T is temperature. And new symbol can be found here, E sub F. E sub F is called the Fermi energy or Fermi level. And this value indicates the probability that an available state energy E is occupied with an electron. Okay. So let's do this a simple question. In conduction, this is a conduction band edge. This is valence band. As we have learned, in valence band, many energy states are filled with electrons because these electrons comes from the electron in between two neighboring silicon atoms. So most likely this valence band is filled with many electrons. What about the conduction band? There is energy states available and each energy states are filled with electrons. This electron coming from the, originally it comes from the electron for these covalent bonds, but however, at room temperature, because of the externally applied thermal energy, this electron becomes free. So this electron has been taken in this energy state. So again, the y-axis indicates the electron's energy. So once electron is sitting in this covalent bond, then it has a lower energy. However, once it is become free, which means it is thermally excited, thermally agitated, right? So in terms of energy, it has much higher energy level. So in conduction band at a certain energy state, that free electron can be found. Okay, now question is, what is this guy? EF, E sub F. So the physicist Fermi said of F of E indicates the probability of finding out an electron at energy state. And what about the energy level that I'm interested in is equal to Fermi energy level? Let's plug in the E sub F here in. Here, instead of E, let's plug in E sub F and calculate this equation. 1 over 1 plus exponential 0. What is this? 1 over 2. 50%. F and F. 50%. At energy level, which is equivalent to the Fermi level, the probability of finding out the electron is 50%. 50% means the answer is at energy state, which is equivalent to the Fermi energy level. Can you find out the electron here? Yes or no? The answer is 50% yes, 50% no. In other words, I don't know. Right? So, going back to the energy band diagram for silicon material, valence band is almost filled with electrons. But in conduction band, compare against the status of valence band, conduction band is almost empty. It's hard to find out the electrons. Only tiny amount of electrons are there. Well, some student might ask this kind of question. You said the total number of electron, maybe without any donors and acceptors, that is 10 to the 10 per cubic centimeter. That is 10 billion electrons. That's not nothing. It is too much, too many. And my answer is like this. And estimate how many electrons are there in valence band. Previously, we estimated atomic density of silicon. What was that? We draw the unit cell, right? And we estimated how many, atoms are effectively included in this unit cell. And it turned out that total effective number of atoms within a unit cell is 8 and divided by the unit cell volume, right? And it turned out that atomic density is 5 times 10 to the 22 per cubic centimeter. And silicon atom has 4 electrons per silicon atom, but silicon atom's density is 5 times 10 to the 22. So you can estimate total number of electrons, right? So 4 times 5 times 10 to the 22. So 2 times 10 to the 23 per cubic centimeter. 23, okay? So 1 cubic centimeter, 10 to the 23 times 2 electrons are available. But in conduction band, the total number of electrons available is simply 10 to the 10. Take a look at, compare the number 10 to the 10 versus 2 times 10 to the 23. Which one is higher? Now you may understand that 10 to the 10 is very nothing compared against the total number of electrons in valence band. Okay? Even though I'm talking about 10 billion electrons in conduction band, which will be the main player to flow current in semiconductor devices, that's true. However, the total number of electrons to build up the silicon crystalline material is 2 times 10 to the 23 per cubic centimeter. In that sense, the number of free electrons or the number of electrons available in conduction band is nothing compared against the total number of electrons in the valence band. Okay, now let's do this. Going back to the Fermi function. said if I plug in E sub f in this Fermi function, that is 50%, which means at this energy level, the probability of finding out the electron is half, 1/2. So E sub c, E sub v, for pure silicon material, there are a bunch of electrons, 2 times 10 to the 23 per cubic centimeter, right? And here 10 to the 10, but it is nothing compared against the 2 times 10 to the 23. So say nothing. Here many, nothing, many, nothing. Y-axis indicates energy of electron. At which energy level the probability of finding out the electron is 50%? You find out the specific energy level, which is E sub f. Where is it? No electrons at this energy level. Many electrons at this energy level. Maybe here, if you pick up any energy level within the valence band, then your F of E, meaning probability of finding out the electron, is about 100%. It is approaching to the value of 1. What about here? Any energy level corresponding to the conduction band, then probability of finding electron is approaching to 0. Maybe 2%, 1%, 0%. My question is, which energy level is corresponding to the 50% probability of finding an electron? The answer would be here. Because no electron, any electron. So mid gap, in the middle of it, this energy state would be corresponding to Fermi energy level. So if I draw it again in a simple shape, the Fermi energy level of pure silicon material can be found at the mid gap. So we know the band gap energy is 1.12 electron volt. So this energy difference, EC minus EF, is 0.56 electron volt. Well, actually, this is not correct perfectly. However, approximately that is true. So E sub F for pure silicon material we found in the mid gap of the energy band diagram. So mid gap, in the middle of the energy band gap. Mid gap, and find out the E sub F, Fermi energy level. Okay. So now let's finish the leftover in this slide. Once E is much greater than E sub F, in other words, E minus EF is approaching to the infinity. And what is the value of the F of E under this condition? Well, E minus E sub F is going to plus infinity, then this exponential stuff will approach to the plus infinity, and 1 over infinity means a 0. Okay, so this equation, mathematical equation, shows again y-axis indicates energy of electron. So there are many energy states available in conduction band. So if you're going up and up, maybe this guy, there would be a single electron available, but the probability of finding out maybe very high energy state would be almost 0. It is less likely to find out the electron at this very high energy state in conduction band. But if you go down here, maybe at this energy state, the probability of finding out electron at relatively lower energy state in conduction band would be slightly higher than zero value. In other words, say suppose at 0.1, which means most likely you will find out electrons near the conduction band edge instead of the upper level of the conduction band. Okay? So this Fermi function indicating the probability value of finding out an electron at a certain energy level is well describing how electrons are stated out in conduction band. Going back to the baseball stadium again, the big data analyst guy has developed, let's use a CCTV to calculate the probability of finding a person in a certain chair. Maybe the same function can be found by physicist Fermi. So this Fermi function looks complicated, right? So this Fermi function is the right thing to estimate the probability of finding an electron in energy state in the conduction band. Okay? All right, the second one, limit E minus EF minus infinity. Then what would be happening here? So here E minus EF going toward the minus infinity, then this guy will become 0, right? Y is exponential x, and x is, if I draw it, x, y, is like that. If this x is approaching to the minus infinity, y value becomes 0, right? It is asymptotically approaching to the 0 value. So here 1 over 1 plus 0. So 1. 1 means 100%. Which means in energy state imbalance band, if you move downward more and more at this energy state, the probability of finding out electron at this energy level is 100%. Okay? So with a probability of 1, you always, I would say, always find out an electron in the lowest energy state in balance band. Because of what? Because the Fermi function says the probability of finding an electron at very lowest energy state in balance band is approximately 100%, 99.9999%. So we can say that, we can claim that the free electron found at lowest energy state in balance band is 1. So this Fermi function is a good tool to estimate the probability of an energy state E is occupied. Okay. So I guess all of you had a well-tuned and synchronized with my understanding how the Fermi function is working to describe the probability of finding an electron in valence band as well as in conduction band. Okay, I guess let's have a short break time. I guess we need some break time for 5 minutes. So I will come back to 25. I will come back to 25. So take a short break time. Okay, so the very last 15 minutes I'm going to spend to explain the Fermi function as a function of temperature. So um, let's switch into the pen. Okay. So here the analytical form for Fermi function is described here, but here you can find out another parameter to describe Fermi function, that is temperature T. K is a Boltzmann constant, as the name itself has indicated, constant, right? So K is constant. So here only two variables, E and T. Usually for given, temperature T, for example, at room temperature, the T is 300 Kelvin. So here, we remember that in the very first slide that we have learned today, KT or KT over Q, thermal voltage, that was a 26 millivolt. So KT is corresponding to 26 milli electron volt. You know this is a prefix 0.0626 electron volt. So for given temperature, the Fermi function can be described as 1 over 1 plus exponential energy E minus EF over 0.026 electron volt. However, the DRAM module and flash memory, they are working at different temperature, right? So we need to understand the function, the Fermi function as a temperature, as a function of temperature. So herein, if temperature T is 400 Kelvin, or this guy's temperature is 300 Kelvin, that is, T is 200 Kelvin and 100 Kelvin. And what if the T is 0 Kelvin, everything is frozen out, then the Fermi function curve be step function like. So here, abruptly switching down to 0. Okay. So in your textbook, there is an example how to draw this f of v versus temperature, f of E versus energy. Here, instead of energy, he used the E minus EF. So once 0 value is, means energy is EF. So when energy is equal to Fermi energy level, the x-axis is corresponding to 0 value. Anyhow, so as a function of temperature, T is 0, 100, 200, 300, 400. He has drawn the Fermi function. Okay, so there is a MATLAB code in the example. So please type in the MATLAB code. Then you will see this class on your screen. So if you have some time, please do that. So now, I have just mentioned that we should use MATLAB to draw the plots for Fermi function. But another physicist, Boltzmann, has developed his own approximation method to make the very complicated shape form of Fermi function very simple and simple. His approximation method is quite simple. Once the energy level or energy state is quite away from the Fermi energy level, so imagine the energy band diagram again here. The Fermi function for pure semiconductor silicon material, EF is positioned in the mid gap, right? So if energy state that I'm interested in is suppose that here, and this E minus EF is higher than 3 times KT. So here at room temperature, KT is a 60 milli electron volt. And band gap energy is 1.12 electron volt, and this KT is 0.026 electron volt times 3 means just less than 0.1 electron volt. So if I'm interested in this energy level, or if I'm interested in this energy level, which is away from the mid gap by 0.3 times kT, then that very complicated Fermi function, again, if I write down it again here, E minus EF over E. This complicated equation can become simpler format, this one. So how do we derive this simple equation? So going back to the calculus class in the freshman course in undergraduate school, we have learned this one. 1 plus exponential x is approximately equal to the exponential minus x if this x is x is much here, exponential to the x is much higher than 1. So if this term exponential to the x is higher than 1, then this whole shape can be rewritten approximately as exponential minus x. So going back to the Fermi function here again, so if here E minus EF over KT, that is corresponding to x, right? So exponential x is higher than 1. So to meet this inequality, I guess E minus EF should be higher than 3 kT, which means this x value is 3. Then we can claim that exponential to the 3 is much higher than 1. So as you know, exponential is approximately 2.7, right? So 2.7 to the 3, or simply 3 to the 3 is a 27. So 27 is much higher than 1. So that's safe, right? So E minus EF is higher than 3 times kT thermal voltage. Then Fermi function, the complicated shape of Fermi function can become very simple as exponential minus here, exponential to the minus E minus EF over kT. So whenever you are estimating the probability of finding an electron at a certain energy level, which is way away from the Fermi energy level, and this amount of energy difference is higher than 3 times kT, then you can enjoy this Boltzmann approximation. Okay. On the second line, similarly, if your energy level that you are interested in is away from the Fermi energy level, more than 3 times kT, then another form of the Boltzmann approximation can be used. Herein, if 1 plus exponential x, this format can become 1 minus exponential x by binomial expansion. I won't talk about too much details, the derivation step from here to there. So if you're interested in it, and please go back to the calculus in Korean, 미적분학 calculus, and you will see this equation. But you don't need to spend too much time. It's a waste of your time to understand this equation. Just remember it once. If x is a small exponential, minus x is much smaller than 1, then you can use 1 minus ex instead of 1 over 1 plus exponential x. Okay, so if the energy state that you're interested in it is way away from the EF, at least by 3 times kT, then Fermi function can become simpler as 1 minus exponential x minus EF over kT. Okay, so using this Boltzmann approximation, we will study, we will find out. Where's my pen? The reason why we are studying Boltzmann approximation is we would like to figure out this equation and as a function of energy. We know the total number of electrons in pure semiconductor material, that is 10 to the 10 per cubic centimeter. We know this number. But my question is, at each energy level, how many electrons are available? Going back to the energy band diagram again here, we know the total number of electrons within the conduction band is 10 to the 10 per cubic centimeter. However, my question is, at this specific energy level, how many electrons are sitting in this specific energy level? And what about this energy state? What about this energy state? What about here, here, here? So you should figure out this function, N of E, the electron concentration as a function of an energy level. What is this question? Going back to the baseball stadium, once you know how the chairs are designed, and on each chair, how long a person can be secured, right? So times probability. Then you will guess number of people on each chair, baseball stadium. So same thing can be applied to estimate how many electrons can be found at each energy state. So for that purpose, we have learned the density of state, and now we have just learned the Fermi function indicating the probability of finding an electron. And since this probability of finding an electron, that equation is quite complicated as a 1 over 1 plus exponential, blah, blah, blah. That format is kind of a disaster to do some integration, to do the derivative stuff. So we need a certain approximation. That is Boltzmann approximation. Okay. Now we are almost ready to guess the N of E. Okay. Right. So N of E. We have simplified the Fermi function with the help of Boltzmann approximation. Okay. So now here, one more information that I want to say is the probability of finding an hole instead of electron. So the probability of finding a hole is quite easy. There is a certain energy state in conduction band. Okay, there is a conduction band H, and there is an energy E1. So once you find out the probability of finding an electron in this energy level at E1, then you will spontaneously estimate how many holes are available in the same energy level E1, because 70% of probability value to indicate the electron's existence rate. Then the other 30% would be for holes existence. Okay. Therefore, once you know the probability of finding an electron, then the probability of finding a hole is quite simple. 1 minus f of v. Okay. So if this is 70%, then the probability of finding a hole is 1 minus 0.7. That is 30%. Okay. So here, the probability that a certain energy state is empty means a certain energy state has hole, or that certain energy state is occupied by a hole, is 1 minus f of v. In f of v is the probability of finding an electron, right? So 1 minus 100% minus probability of finding an electron is identical to the probability of finding a hole. Okay, so you can write down the equation for finding a hole. Okay, so that's the Boltzmann approximation, right? And now we are almost geared up with two gears, one of which is density of state, the other of which is probability of finding an electron. Why these two gears are required? We have arrived at this point to estimate the electron concentration for a given energy state. So again, on the left-hand side, you can see that for a certain energy state in conduction band, here is sub C, right? So there are many energy states. There are many chairs in a row in baseball stadium, okay? So at this specific energy level, how many electrons can be found here? On the right-hand side, you can see the distribution of energy, distribution of electron concentration as a function of E. So at this very high energy state, the number of electron is quite almost zero, nothing, right? Why is that? Electrons prefer to have a lowest energy state in the conduction band. Okay, so as we have intuitively understood, most of electrons will be found at the energy state near to the conduction band edge. So in the end here, N over E, the shape is like that. So which means that at a very high energy state, the number of electron is almost zero, but at energy level very close to the conduction band edge is almost, maybe this value is quite equal to the n sub I 10 to the 10, right? Not exactly to the 10 to the 10. So to get to the, so in order to make a conclusion that most of the electrons can be found near to the conduction band edge, we need two weapons, two gears, density of states and probability of occupancy. In other words, Fermi function. Okay, so for how the energy states are created in the conduction band, TOS will give us the hint. And at each energy state, from the density of state, we will calculate the probability value of finding an electron at each specific energy level. Then we will end up with the total number of electrons for a specific energy state. How to get it? The answer is density of state times Fermi function. Then you will get the electron concentration on each energy state. So how do we get this? Going back to the baseball stadium again, you remember this figure as I draw. At a certain energy state, there are six chairs, but the CCTV tell us only 3 chairs are secured by people. So 50% chairs are secured with a person. So effectively 3% can be found at this energy state E sub 1. And we will repeat this work for different energy state. Then we need to know how the seats are designed. So at the energy of E sub naught, only 4 chairs available. Then we need to record how long each seats are secured with the people, say 30%. Then 1.2 people be found at energy level of E naught. So these kind of things, this process should be repeated for all the energy state. In other words, once you know this energy, the electron concentration or the people's density as a function of energy, then you can sum them up. So from energy is 0 to infinity, which means integration of N over E with respect to the energy is equal to the total electron concentration N. Okay, so we in the last couple of weeks we have learned that this total electron concentration is governed and controlled by donor concentration or acceptor concentration, and it turned out that the total electron concentration N is well controlled by the dopants. Now today, for the last 3 hours, we have spent the whole hours to understand the electron concentration as a function of energy state in conduction band. For more details, the density of states that we have learned last week, and today we have learned the Fermi function to get the probability value for each specific energy state. Okay. Then once we multiply density of state time with probability of occupancy by electrons, then we will end up with a carrier distribution or electron distribution in conduction band. Okay. So I guess it's time's up. I guess please read out the chapter 2 to understand the equilibrium distribution of electrons in conduction band with the understanding of density of states and probability of occupancy. Then in the upcoming week, I'm going to briefly review the density of states and probability of occupancy. Then we will keep moving forward to understand how free electrons to flow current in MOSFET, PN junction diode, MS diode. Those free carriers are distributed out in a conduction band. Okay, so I guess please have your own studying review time for all the materials that I've talked today. And as I told you, the recording movie clip will be posted on iCampus maybe a few days later from now, because I have to download it from cloud server. So it would take a few days to convert this recorded movie clip into MP4 version. So I don't understand fully how come the 1 day is necessary to convert the file. But anyhow, many lectures is this real in real time recorded, so it takes a few days. All right. Okay, that's all, and that's all for today's lecture. And have a review time, please. Okay, that's all. And if you have any question, leave a text message in chatting room, or you can use a bullet board in iCampus. Okay, that's all for today's lecture, and see you next week. And just for undergrad student who is taking my undergrad class, integrated circuit, please wait for another 10 minutes. So I'm going to begin my lecture for integrated circuit at 3 p.m. So all the graduate students, you can leave my meeting room. That's all for the solid state physics class. Okay, that's it. I'm going to stop here.